Hello, my name is William Trexler. This presentation is part of a project for the Nuc-495 capstone course for Thomas Edison State University's February 2016 semester for Group Alpha. There have been several past events which have helped to shape the nuclear industry in areas such as regulation, emergency readiness, plant design, operator training, public opinion, and even the formation of the Institute of Nuclear Power Operations. Our group will cover the following events: the 3 Mile Island Unit 2 accident, the Chernobyl accident, the Browns Ferry fire, and most recently, the Fukushima Daiichi event. As part of our Events That Shape the Industry presentation, I will be covering the first of 5 phases, the accident at 3 Mile Island Unit 2, which occurred in 1979. The 3 Mile Island site is located in Middleton, Pennsylvania, which is about 100 miles west of Philadelphia. 3 Mile Island Unit 2 was a Babcock & Wilcox pressurized water reactor outputting 880 megawatts electric. Below you can see a photo taken of the site with Unit 2 in the foreground and Unit 1 operating in the background. Following initial construction, Unit 2 attained initial criticality on March 28, 1978. Exactly 1 year later, still in its first fuel load, TMI Unit 2 experienced a chain of events leading to a partial core meltdown. So how did this all happen? First, let's take a look at some basic plant design features to understand. In a pressurized water reactor design, one general way to classify piping and systems is by primary, the radioactive side, and secondary, the non-radioactive side. The primary system includes the reactor core, the reactor coolant pumps, the pressurizer, and the primary side of the steam generator. TMI Unit 2 had 2 primary loops, each with 2 reactor coolant pumps to circulate the water from the core to the steam generators and back to the core. This provides cooling to the fuel. The pressurizer, which is connected to the primary loop, maintains pressure in the primary system at about 2,150 pounds and acts as a surge volume to accommodate for thermal expansion. There is a steam relief on the pressurizer to prevent overpressurization, marked as the PORV, or Power Operated Relief Valve. As you will see, the Power Operated Relief Valve is one of the key components in this accident. The steam generator, in this case a vertically mounted one, provides for the heat exchange of primary to secondary water through U-tubes. Non-radioactive steam is generated and sent to the turbine. The condensed steam is reheated and sent back to feed the steam generator through the condensate and feedwater systems. For the most part, primary systems are largely located within containment, also known as the reactor building. To understand what happened, we need to analyze the chain of events. The initial conditions are as follows. Unit 2 is operating at 98% power. There are 2 licensed operators in the control room, and the shift supervisor is in his office adjacent to the control room. The shift foreman and 2 auxiliary operators are working in the turbine building on the condensate polishing system, a series of resin beds designed to clean up the condensate water. At 0400, all in-service condensate polishers isolate, resulting in a loss of condensate and subsequently feedwater flow. This causes the main turbine to trip and reactor power to automatically decrease. 3 emergency feedwater pumps started, which would normally align automatically when level in the steam generator reaches 30 inches. However, block valves in the feedwater line were closed. Even though there were indicating lights in the control room, operators failed to notice this. Due to the reduced cooling in the primary pressure reached 2,255 pounds, at which point the power-operated relief valve opens as designed. As the reactor is still generating power, pressure continues to increase. At 2,355 pounds, the reactor automatically scrams, placing all control rods on the bottom of the core. As pressure on the primary decreased to the point at which the power-operated relief valve should close, an indicating light in the control room went out, signifying that the open signal has been removed. However, this alone does not mean the power-operated relief valve has closed. The operators assuming that the power-operated relief valve had closed is what will lead to a continuous discharge of coolant over the next 2.5 hours. At this point, an operator successfully starts a second high-pressure makeup pump to inject water into the core. This was to combat lowering pressurizer level. With continued heat input and no feed water, both of the steam generators now boil dry. Operators are still unaware that the power operated relief valve is open, which is driving their pressure, temperature, and pressurizer level changes. As primary pressure drops to 1,640 pounds, a safeguards automatic initiation occurs, resulting in another high-pressure makeup pump starting. As pressurizer level was rising to a level operators were not comfortable with, they bypassed safeguards features by throttling emergency core cooling flow. Not realizing they were actually experiencing a loss of coolant accident, operators began taking steps to recover from the scram. As pressurizer level went high off scale, while pressure continued to drop, operators re-established letdown or discharge flow, further reducing total inventory. Operators incorrectly assumed the instruments measuring pressurizer level were malfunctioning, continuing to drain the primary system. With the power operator relief valve still open, the drain tank the power operator relief valve relieves to continued to fill and overflow, spilling thousands of gallons of primary coolant directly into the reactor building. One thing of note is that several alarms per second are occurring in the control room. With so many annunciators lighting up at the same time, their value as an operator aid has diminished. Still not understanding that the power operator relief valve is open, operators are left analyzing the fact that pressurizer level is high and primary pressure is low at around 1,100 pounds. Believing that some of the U-tubes are leaking, the operators then isolate one of the steam generators. Due to severe vibrations in the reactor coolant pumps, operators secure the remaining reactor coolant pumps. In reality, water in the primary was reaching saturation conditions, meaning the reactor coolant pumps were trying to process a water-steam mixture. At this point, the upper portions of the core were becoming uncovered, forming superheated steam in the core. Saturation conditions had been met. Fuel temperature rises and begins to fail. A partial meltdown has occurred. A day shift supervisor arrives on site and immediately identifies that the power operated relief valve is open. Then operators take action to close the power operated relief valve and begin appropriate procedures to recover loss of coolant and place the plant in a stable condition. Here are some of the major contributing factors to the severity of this event. Plant equipment was operated at degraded conditions for extended periods of time. Operators assumed meter readings were faulty instead of investigating. This was because they were on a mindset for a specific casualty and were blinded to the other possibilities. Emergency operating procedures were event-based and did not fully allow operators to analyze conflicting plant parameters where more complicated or multiple casualties were occurring simultaneously. There were weaknesses in operator training. Operators misunderstood plant behavior, including the thermodynamic properties of steam and water. This prevented them from understanding saturation conditions were occurring. And finally, the beginnings of this event were similar in nature to an event at Davis-Besse just a year and a half before. If lessons learned had been shared with all plants in the industry, this disaster might have been avoided. Here were some of the immediate effects of the accident. The governor of Pennsylvania issued an evacuation advisory on March 30th concerning pregnant women and preschool children within 5 miles of the plant, to about 4,200 individuals. However, around 144,000 actually evacuated. Nearly all evacuees had returned by the end of April. During the event, 3 utility personnel received elevated levels of exposure, and 1 received non-life-threatening exposure exceeding federal limits. Later that year, 6 individuals received high skin doses while performing work in the plant on valves leaking water from the March 28th accident. Approximately 300,000 gallons of radioactive water had leaked to the reactor building from the primary. About 2% of the radioactivity released from the fuel during the meltdown was released to the environment in the form of noble gases. From March 28th at 0400 to March 29th, 265,000 gallons of contaminated liquids were released to the Susquehanna River through the industrial waste treatment system. Due to the extreme temperatures, most of the fuel in the reactor shattered or partially melted. After reaching over 2400 degrees Kelvin, most of the molten materials relocated to the lower core region. Eventually, the molten material came to rest on the bottom head of the reactor vessel. This melted mass was ultimately contained in the reactor pressure vessel as it did not reach melting temperatures. So what were some of the ways the 3 Mile Island event changed the industry? Many plant design changes were implemented into existing plants to assist with accident mitigation capabilities. Support for nuclear projects dissipated as public confidence in nuclear power was disrupted. Plans for new plants were suspended, while some plants under construction were scrapped. Improvements to the control room aimed at helping operators identify problems were implemented. With 3 Mile Island, there were too many alarms and lights going off at the same time to humanly discern which one should take priority. Operator training was improved dramatically to include more fundamentals. Simulators designed to mimic each specific plant were utilized as a training tool for accident scenarios. Emergency operating procedures were rewritten as symptom-based, not event-based, so that one particular indicator could mean more than one specific casualty was occurring. Additionally, improvements to the overall emergency preparedness of city, state, and federal officials were made, as well as notification timelines established for the operator. Regulatory oversight by the NRC was improved, revamping inspection standards, reports, performance determination, and vulnerability analysis. And finally, the Institute of Nuclear Power Operations, also known as INPO, was established. Today, INPO strives to promote excellence in operations, as well as provide an easy way for plants to share lessons learned. This concludes my presentation on the accident at 3 Mile Island and its effects on the nuclear industry. I will now turn the presentation over to Leonard Bradshaw for Phase 2. Leonard will be discussing Part 1 of the Chernobyl accident. Thank you.